The definition of continuity: a function that can be graphed throughout its domain with one continuous motion of the pen, which is without lifting the pen, is an example of a continuous function. Diagram A and B are continuous since they can be drawn without lifting your pen. Diagram C and D are discontinuous because of the breaks in the function. So we could see here that there is a break in the function. Definition of continuity at a point x equal to c. A function, f of x, is said to be continuous at x equal to c if it satisfies the following three conditions. The first condition, fc exists. The second condition, limit x approaches c, f of x exists, which is limit x approaches c from the right equal to limit x approaches c from the left. The third condition, limit x approaches c for the function f of x is equal to the f of c. Continuity at points p, q, and r. A function y equal to fx is continuous at interior point q, here, of its domain if limit x approaches q, fx is equal to fq. Second, a function y equal to fx is continuous at a right endpoint p of its domain if limit x approaches p from the right is equal to fp, here. So it means the graph has right hand limit. The third one, a function y equal to fx is continuous at a left endpoint r of its domain if limit x approaches r from the left is equal to fr. So we could say that the graph has left hand limit. Then, if a function y equal to fx is not continuous at a point u, we say that f of x is discontinuous at u, or u is a point of discontinuity of f of x. Example 18. Find the interval of x for which f is continuous. We know that the interval of x for which f is continuous is called domain. So basically, we just need to find the domain for all the functions needed. For example B, function is set to x minus 5. So to find the domain of this function, I'm going to sketch the graph. So the graph is going to look like this. So to sketch the set graph, we just simply making the value inside the set greater than or equal to 0, since we know that the value inside set cannot be negative, it must be positive. So 2x minus 5 must be greater than or equal to 0. So 2x must be greater than or equal to 5. So x must be greater than or equal to 5 over 2. So x equal to 5 over 2 will be situated here. And then the value of y is equal to 0. So y0 is basically here. So the starting point for the set graph is here. And then the graph will look like this. So the domain for the function is 5 over 2 infinity. So we could say that f is continuous at 5 over 2 infinity. Example 22. The function f is defined by f of x equal to 1 plus ex for x less than 1, 3 x equal to 1, 2 plus e minus x for x greater than 1. Find the limit x approaches 1 from the left and limit x approaches 1 from the right. So limit x approaches 1 from the left. So to choose the correct function, I'm going to draw a number line separating the function at x equal to 1. So exactly at x equal to 1, the function is 3. When x less than 1, the function is 1 plus ex. When x greater than 1, the function is 2 plus e minus x. So when we would like to find limit x approaches 1 from the left, so the function is 1 plus ex. And we could just simply substitute x equal to 1. So we're going to end up with 1 plus e. And then I'm going to find the limit x approaches 1 from the right. So x approaches 1 from the right, the function is 2 plus e minus x. Then substitute x equal to 1, which will give us 1 plus e. So, since the limit x approaches 1 from the left is 1 plus e, and limit x approaches 1 from the right is also 1 plus e, so we could write it as limit x approaches 1 for the function f of x is equal to 1 plus e. Next, hence, discuss the continuity at x equal to 1. So if the function is continuous at x equal to 1, it's going to fulfill all the three conditions. So the first condition, if it's continuous at x equal to 1, f1 must be exists. So f1, we must find the function that has equal sign. So the function is equal to 3. So we could say that f1 equal to 3. So it is exists. So we already fulfilled the first condition. The second condition saying that limit x approaches 1 from the left must be equal to limit x approaches 1 from the right. So we already find the value of limit x approaches 1 from the left and x approaches 1 from the right, and both are the same value, give the same value. So we could write that limit x approaches 1 for the function f of x is equal to 1 plus e. So we already fulfilled the second condition. And the third condition saying that if it's continuous, f1, the value that we get from the first condition, must be equal to limit x approaches 1 fx. But since it does not equal, because for f1, we get the value is equal to 3, but the limit x approaches 1 f of x is equal to 1 plus e. Since it's not the same value, so we could conclude that fx is not continuous, is discontinuous at x equal to 1, because the third condition is not fulfilled. Example 20, given that fx equal to ax plus 5 for x less than equal to 1 and x squared minus 1 for x greater than 1. If fx is continuous for all values of x, find the values of the constant a. If fx is continuous for all values of x, so it must be continuous at x equal to 1. So if it is continuous at x equal to 1, we could apply the second condition saying that limit x approaches 1 from the left is equal to limit x approaches 1 from the right. So if I draw a number line separating the function at x equal to 1, so when x less than equal to 1, the function is ax plus 5. For x greater than 1, the function is x squared minus 1. So when x approaches 1 from the left, the function is ax plus 5. And when x approaches 1 from the right, the function is x squared minus 1. By using the second condition, I'm going to substitute x equal to 1 to find the value of a. So when we substitute x equal to 1, we get the value of a plus 5 equal to 0. So a equal to negative 5.